Hi everyone, and welcome to another episode of Mr. Carlson's Lab. I picked up another really neat electronic device for us to restore and bring back to life together. It's an older piece of test gear from the late 30s to early 40s era known as the Supreme Vedolyzer. You know, with a name like that, it's gotta be good. If you had one of these things on your service bench way back when, people would come into your shop and go, wow, check out the high-tech piece of gear. It's 3 pieces of test equipment all in one case. It's an oscilloscope, a wave meter, and a vacuum tube voltmeter all within one device. So we're going to open this thing up, we're going to check out the design on the inside, we'll get an idea of what the engineers were thinking of when they put this thing together, then we're going to restore this and use it to service other pieces of test gear, older radios, and the best part is we're going to even use this old piece of test equipment to service modern devices as well. So this should be a lot of fun. So let's bring this thing back to life. Here you are, sitting at the bench with me. So let's take a look at what we're up against. Well, so far I can see that the face is in pretty nice condition. It's missing a few things, and somebody's put a BNC on the bottom here, it looks like. Missing a knob right here, and a small screw in the bezel. But other than that, the face is looking like it can be cleaned up really well. The wooden case, it's another story. It's going to need refinishing. And just taking time with the case alone is going to take a long time. So in this video, what we're going to do is just focus on the electrical restoration. So as I mentioned in my other videos, I buy these things and I haven't looked inside this. I don't know what's inside other than, peeking through the top holes in the case there. It has some vent holes in the wooden case. I don't know anything about this. So when I purchase these things, I put them aside so that we can experience this together. So everything I find out about this thing is exactly at the same time you're finding out about it. There could be, rocks underneath the chassis for all I know at this point. It's pretty heavy. It feels like they could have some rocks in there. So the knobs feel like they're turning okay. Lots of dirt on these. Let's see if these... Well, yeah, they're latching. You see the dust waft off of that when I did that? So they're latching, so that's pretty good. Let's try these ones. Yeah, no problems. A little bit crusty. Not a problem. So it looks like we're off to a really good start here. The meter looks to be in very nice condition. The wave meter is nice and smooth. So some of the things that I see already that I will address is these odd type jacks for the inputs here. So what I'm going to do is, I'm going to remove this because this is in the wrong spot here. This is supposed to be a ground, but what I'll do is I'll nicely fit some BNCs in the area of these jacks. These are really an odd jack. Because I plan on using this. This thing is definitely not going to be any type of a shelf queen. So we're going to use this thing in the future to repair other pieces of equipment. So I want to easily use my probes with this. And, a more common connection for a probe nowadays is a BNC connection. This one here doesn't look very nice. I've got a whole bunch of really nice looking BNC connectors that'll fit right into the front of this here. So it'll look really good. So already we're off to a good start. You see the line cord. Look at this line cord. Could they get any more crusty? Look at this. It's completely decayed. So definitely going to be getting a new line cord. I'll probably just end up cutting that off here in a moment. So it looks like the only thing I need to remove to get into the case of this is all of these Phillips screws around the face of the unit, and hopefully this should just slide forward. I might need to cut off the line cord on the back side of the unit just because it goes through the backside. What I'll do here is I'll just turn the unit around and I'll show you what it looks like on the back. Here's the back side of the Vedolyzer, and as you can see, not a whole lot to it, just a metal cover. So while I'm here, just get rid of that. This horrible crusty cord can go in the garbage. So what I'll do is, this looks like it has flathead or slot head screws on the back, and the front looks like it has Phillips. So I imagine This has been out of the case before, and it's probably those screws aren't original, so I'll replace those screws with some slot-headed screws on the front to make it look just a little bit more original when this goes back into the case. The case itself is in pretty rough condition here. I'll just tip this up so you can see it. Hopefully it won't be too overexposed. Yeah, it is pretty overexposed. I'll just bump that down a whole lot. You can see that, it's in pretty rough condition. Nice looking case. So again, just needs to be stripped. And maybe I'll even color this the same as the old time workbench. So maybe I'll stain this to the same color. That'd be kind of neat to have that fit in. Look like it really belongs on the bench. It's a little bit darker than this stain, so when that comes to that time, I'll worry about that then. So what I'm going to do now is turn the unit back around again. We'll look at the face of the unit, and I'll try and slide this thing out, and we'll take a closer look at the chassis and see what we're up against. Already what I can see through the back here is it looks pretty clean inside. So hopefully looking through this isn't deceiving. All right, let's see if we can get this thing out of the case. A relatively long screw. Let's put this down here. Get all of these out of the way. Again, I'd really like to replace these with a flathead screw of some sort. Something that would match the unit a little bit better. Usually when these are tightened down, they really mar up the face. This isn't too bad. Alright, that seems like that's it. Let's see what happens. You can feel the weight of the face is kind of dropping down on the screws. It kind of happens with these. You can see how it's already slid down a little bit. Alright, let's see if we're in. Haha, it's coming out. It's definitely coming out. Let's get this on its side here. You can see in the side, I can already see some tubes and wires and stuff. And the chassis has a little bit of surface rust on it. So what I'm going to have to do here is move this out of the way so I can pull this right out of the cabinet. This is hanging over the edge of the bench right now. So what I'll do is I'll just pull this out and get the wooden case out of the way, and we'll take a closer look at the chassis and see what we're up against. Here's a closer look at the upper portion of the chassis, and as you can see, it looks like it's in really nice condition. Looks like they've chromed the chassis, but dirt and debris has been settling on the top side of the chassis for years and years now, and that's caused some surface rust, so it'll be interesting to see how well the chassis cleans up on the upper side. You'll notice that they've mounted the power transformer on an angle, and they've used some brackets here, which is kind of interesting. You can really see the engineers were thinking back then. They wanted that transformer to last a really long time, and they wanted it to cool properly. A lot of companies took transformers like this and just mounted them straight down to the chassis, so basically there was a square cut on the chassis, and they just bolt the thing right down to the chassis, so there is no way for the transformer to cool properly. By having this transformer on an angle like this, it'll allow air passage past the transformer, so it'll cool a lot better. And there's a square cutout below the transformer as well where the wiring goes through, so that'll allow air passage from the bottom side of the chassis to go around the transformer as well. So there's an air passage here, and there's an air passage under here from the underside of the chassis. So you can see there's quite a bit of thought that went into this. Lots of tubes on the upper side of the chassis here, 2 large tubes here, 1 here, 4 over here, 1 there, and then we have the CRT. So lots and lots of tubes here. A bunch of batteries that have been soldered into place. So those batteries are for the VTVM, and these will definitely need to be replaced. You see a wax capacitor clamped to the face here, that'll have to go. Another capacitor over there that'll have to go. This one here looks like the high voltage filter capacitor. You can see the insulated standoffs there. Another capacitor here. And it even looks like there are some capacitors in the side of that switch over there. You can see right down in there. So we'll take a closer look at that stuff here quite shortly. So all in all, it's already looking like a bit of a job for a restoration here, but that won't stop us. We'll get going and we'll make this thing operate again. So what I'll do now is I'll flip this thing upside down here so we can take a look at the bottom side of the chassis and we'll really get an idea of what we're up against. Well, looking at the bottom side of this chassis, the only thing I really have to say at this point is, wow. There's a whole lot of work to get this thing running again, and I would imagine that's probably one of the reasons why you don't see a whole lot of these things around anymore. So to give you an idea, the way the camera's looking at this right now, you really can't get an idea of depth all that well, but this is my hand down into the chassis, and these are all isolated boxes. And as you can see, that's about the width of the box. And way down inside those boxes are capacitors, so I'll stick my finger right down in there. So it's about that deep into the box. That's me touching the side, and that's me touching the capacitor. So yeah, it's about that deep. And that's the top capacitor, and then there's another one on the bottom here, and they're in each box. Now, looking at the construction on the bottom side of this thing, this side here and this side here are spot welded to the actual chassis over here. Now, on the top side, there's a bunch of screws. You can see these screws. I don't know if you can see that. There's a bunch of screws there. See these screws right here, and there's a little bit of a space down there at the bottom. So what that means is this is an entire, it's kind of like a floating chassis. You can undo those screws and you can take this middle section out minus the sides. The sides are spot welded in. So this would slide between these two little walls here. Now, in order to get this section out, what I would need to do is disconnect all the wires that run through the sidewall and all the wires that lead off. And that's including all the wires in the front here that lead off this little chassis that's screwed down into the main chassis. So there's an incredible amount of work to get these components out. Now, you might be saying to yourself, well, why not just get an extended tip on your soldering iron or just go down into here? There's a little bit of working room in there. Well, what they've done, these tube sockets that you see down here, I don't know if you can see a little bit of it right there. See this right here? Right down at the bottom, that little black thing that you see right down there? Break that off. See how I broke that off? Those are rubber grommets. What they've done is they've put rubber washers between the tube sockets and the chassis. So they've made somewhat of a shock absorber mount for these vacuum tubes. And the reason that they did that back in the day is because this thing was sitting on a service bench. And usually there's a bunch of people working at a service bench, and if somebody drops something on the service bench down the line a little ways, that little bit of vibration can carry over and get into the tubes here, and it can cause, erroneous readings and things like that. So they made shock absorber mounts for the tube sockets. So all of those little rubber washers, and you can't really see that down in there. You see that one, how badly decayed that is down there, right? So all of those rubber washers are all decayed, and these tube sockets are kind of just rattling around. I think there's a loose screw on one of them. Yeah, you can hear that. You can actually see it right down in there moving. So the screws are all loose on the tube sockets. So I really need to get this whole entire section out of here, and I need to fix that tube socket problem. Now you might be asking yourself, why did they do this? Well, what they're doing is they're shielding one stage from the next. This is an incredibly nice design. The way that they've put this together is very nice. Just like the Hallicrafters SX28A, they wanted each stage to be shielded from the next. And as you can see down here, each tube socket is kind of halfway in the middle of each shield. So what they're trying to do is isolate input and output as they're going all the way along, and just keep the stages nice and quiet. Very, very nice design. This is way ahead of its time for the late 30s era. The way that they're doing this and the way that they're thinking with these tube sockets and even the the rubber mounted tube sockets and things like that, they use this practice well past this era. Even with the miniature tubes, they even rubber mounted some of those tube sockets as well in high vibration atmospheres. So lots of work just in this area here, lots of capacitors. Now, I get a lot of people always saying to me, Paul, the foil side of a capacitor doesn't matter. Well, in this case, it matters so much that they didn't even put outside foil on the band end. They actually just blatantly put ground there. So they want you to know what side is supposed to go where, and all of these capacitors are just marked ground. This one here says ground lead, written right on the capacitor here. And when I get these caps out, we'll take a closer look at them. And we'll take a look at the outer foil side of these as well. Now, this is back in the day when the engineers understood how to properly make a point-to-point wiring scheme inside of a chassis. So the engineers, this is what they're familiar with, and this meant a lot. And this is the reason why their capacitors don't even say outside foil. This is so in your face. This side is ground. They want to make sure that they're all in the correct way. And all these capacitors, as you can see, this end here ties to the chassis down here. They knew what they were doing. Everything was installed the correct way. This is a capacitor here. This is a main filter capacitor in a box. This is the way that they made them, kind of a paper box. This is going to have to go. There's more of these kind of paper box style capacitors here. They're long. When I get this little piece of the chassis out, we'll take a look at that. In order to get this chassis out, the amount of work is just incredible. I have to take off all of these wires, all on the face. I have to take off every single knob and every single dial and everything on the face of this unit to get this face off. And in order to change the capacitors that are down inside this secondary box. So you think these boxes here are deep. Look at this one here. It was way down in there. And there's, as you can see right down here, a wax capacitor, and there's another one over here, and that's in another somewhat of a shielded box on the top side of the chassis. So it's another part of the chassis. It's a shielded box, and it is for the wave meter adjustments. So this is way down in there, way down. So that all has to be done. So some batteries here that are either for the meter or for biasing or for something. I'll have to take a look at the schematic here in just a little bit. I managed to find a schematic on this thing, so we'll go through that. Take a look at that as well. Really condensed schematic for this chassis. Lots and lots of stuff. Really busy, this thing. So you can see people have been in here and they've replaced capacitors along the way. And as you can see, the blowholes on the capacitor are gone. This one here is actually shot a lot of the paste inside all over the socket under here. So this is extremely bad. Just lots and lots of work replacing caps. They're just everywhere. Everywhere you look in this chassis is a cap. So, and everyone needs to be put in the correct way and orientated the right way. So it'll be really interesting to see how close to spec this thing will get. See how, how high in frequency we can get this scope to read and everything. It'll be a really neat little project to get this thing going. Just for the fun of it, I took a bit of polish and I tried polishing a lot of the rust off the top side of the chassis. It looked like this before and here and over and here. And it's coming out okay. Yeah, it's really pitted still and everything from that moist dust sitting on the chassis. But when I get this little area out, you can see how this is a little chassis that screws to the top side of this large chassis. And then there's this box over here with the wave meter on top of it that's sitting on here. That has to be removed as well. Again, the work getting this thing apart is just absolutely incredible. The amount of wiring that I have to desolder and just remove the entire face, take off all the knobs and all the little buttons and everything. So just the disassembly, I can imagine, for this thing is going to be a few hours. It really is that incredibly crazy. So It came out not too bad. If I spend some time using the rust remover on the rest of the chassis and maybe some polish and stuff like that, I might even let that rust remover sit on the chassis for an extended period of time and see if it'll help with the pitting just a little bit more. But as you can see, it looks really nice. Like they actually spent the time to chrome this chassis and make it look really, really nice. So hopefully it doesn't look too incredibly bad. I have to do the woodwork on the outer box as well, and the outer box is an incredible amount of time in that. I'll spare you from all of that. So if I can get the chassis looking nice enough on this thing, maybe I'll just leave this thing open for a little while as I take my time to do the woodwork on the actual outer case, and we'll just use this thing on the old-time workbench with the chassis open like this. In order to start disassembling the chassis, I need to take this entire face off. So that means that I need to remove pretty much every knob and dial and everything on the face here. So these chicken head knobs have a little screw in the side here, which makes them relatively easy to get off if they're not seized on the shaft. And these things here you can see one's missing. When I got this one's missing, so I'm going to have to look through my stash of little buttons and see if I can find one here. Let's see if this comes off. Yeah, okay, so there's one. So I'm going to want to put these in a little bowl so that I don't lose any of these. That would be horrible. Let's see if this one comes off. Yep. So, yeah, a little bowl. That gives me a chance to clean all of these up as well. And then when the face is off of this, I can spend a lot of time and polish this face up. So this might actually come out really nice. I still want to put the BNC jacks in here. Somebody's put a BNC in here, and this is directly for the scope itself, it looks like, from the way they've wired this. So they've taken one of the leads off of these here, and they've just run it right over to here. So somebody at one time was at least just using the oscilloscope on this. And then, of course, having the VTVM separately is a nice feature as well. So technically you have a voltmeter and an oscilloscope all in one unit. Now, the wave meter is kind of handy. Wave meter is, again, kind of like an early frequency counter. It's just you look for the frequency by moving this, and then by looking at the meter here, you can tell when you get right to the frequency. Now, I'm not sure if they have this in conjunction with the oscilloscope as well, or just this meter here. In the end, we'll find out, move this thing around, and we'll see how well the wave meter actually works. The entire face is removed off the Vedolyzer, and that alone was an incredible amount of work. Look at all this stuff. There are so many screws and buttons and knobs off to the side. It's really quite crazy. All of these VRs are all loose. So on the back side of the face, let's grab the face here, I left those capacitors on. I had to remove one screw right here because there's a terminal tie strip there, and this was soldered to a VR, and it's the same with this one over here. But you can see just the sheer amount of buttons, knobs, dials, and screws that had to come off. So lots and lots of work. Let's move that off to the side here again. So now that this is off, you can see this little box underneath the wave meter here. So I can move this down. You can see there's a capacitor here. And those are those three capacitors hiding in this wave meter box. And this is also screwed to the chassis. And this is also screwed on top of that other area, this area here, these boxes that I have to remove. So I'm going to mark this. So I'm going to mark the dial on the back side. I'm going to remove the dial. Of course, this is going to need a complete realignment when this is all done. And by getting this dial out of the way, I'll be able to get at these capacitors and replace those caps as well. So as you can see, there's capacitors on these things as well, hiding in behind. See the ones hiding over here, here, and here. This would be absolutely impossible to get to unless you take the face off of this device. So lots of loose wires and connections all over the place. It's going to be lots of fun to put back together, I can tell you that. And now that the face is off, the chassis is all wobbly because, this is pretty much, well, it's part of the structure, holds the whole thing together nice and tight, right? So CRT is just kind of dangling in the breeze up here. So I'll probably end up just taking this out as well, just to keep this safe. I don't want to end up bumping that. So chrome looks nice on the area I polished. So at any rate, I'm on my way, one piece at a time. I've got the wave meter portion out. So really there was just two wires that are attached to the wave meter. One is attached here, and this red wire attaches to a switch that's under here. So this black wire that you see here attaches to this point that was unsoldered, and this runs down through a little rubber grommet, which you can see right here, and that goes under here to that switch. Now I imagine I'm still going to have to take this off. As you can see on the back side here, that runs to this capacitor, and I've already marked the shaft, as you can see there. That'll help me with my alignment in the end. I don't think this has ever been removed. Black mark right there. So when I get in here to desolder these capacitors, I don't want to risk touching this with my soldering iron, so I want this right out of the way. But all in all, this doesn't look too incredibly bad. There's really just 3 capacitors inside this box. So this should rebuild rather easy, and then I can put that back on the chassis. And this box, again, was on top of this other layer here. So now that this is out of the way, I can try to remove the rest of these boxes. So I'm going to have to get in there and mark all the wiring that runs all over the place. Here's one of the wires coming out of that box. Have to mark all the wiring and then try to remove that as a complete assembly. Well, I'll grab the CRT while I'm here. I'll move that out of the way. So this is the CRT. It's not looking like it's too bad. Yeah, it's a little dirty and dusty. The getter spot is a little bit odd looking, but you know, the getter spot in a lot of these older CRTs does look like that. So this is a 3AP1. You can see right there. So hopefully this CRT is working okay. So I can put the CRT back in. If the CRT doesn't work correctly, I can remove the socket. There's a socket at the back here, and there's 2 screws that hold the socket. So basically what I would do is slide the tube back, and then I could most likely remove it out of the top side. So I'm hoping that this CRT is good. Before I put this whole thing back together and you know, get everything all ready, I might just actually test this CRT in another scope just to make sure it is okay, because it is a little bit of a, you know, a procedure to get that out. Now I can move the socket back. I'm not sure if there would be enough room to actually tilt this up and out of the way. Maybe there wouldn't be. So removing the bezel would probably be the way that they would get this CRT out of here. I'm imagining, yeah, that would be it. So I'd have to remove the bezel, and this would slide through the face of the unit. So not a fun job. So yeah, definitely I'll be testing this thing before I put it back in. Find another older scope around here that has this same type of CRT. The base feels a little bit loose. Anyways, so here's hoping that this CRT is good. After much wrestling with this chassis, I managed to get that center portion out. What a job that was. It turns out that these walls are not spot welded to this portion of the chassis here. This wall was sitting right on top of that spot weld right there, and I figured that they had done that. Those walls are just screwed to the side of that center assembly, which makes my life quite a bit easier because I can move this wall and get to that horribly blown up capacitor down there and clean all the goop off of that tube socket. That's a high voltage area down there, and this thing has just sprayed that tube socket. Look at the mess under there. So quite a bit of cleanup there as well. So there's no structural stability left in this chassis with all these pieces gone. This thing is held up and basically just, you know, I've got a whole bunch of little stands underneath holding this in place so I can show you all this. There's a VR with a very long shaft that goes right from the backside all the way to the front, right through the front. I had to remove the nut on that as well and then lay that forward so when I drop that chassis out, I could slide it out like this. Really tight fit. Lots and lots of wires had to get desoldered to get that out of there. You can see all the wires are out of these grommets here and high voltage leads here. These capacitors are disconnected and this whole switch assembly is just hanging down here now. Lots and lots of reassembly to do once that little section is rebuilt. And you can bet that that little section is going to get the best components because that is not coming out again. What a job. Here's that center section removed from the chassis, and as you can see, a lot of work. But it's going to be much easier with this out of the main chassis. So you can see these rubber grommets, which are now, almost like glass. So these are, you can call them rails or buses running along here, and they're tapping the high voltage off of this one here. So the high voltage comes in over here and runs down to the tube sockets through resistors, and you can see there's filtering all over the place. This one down here, this rail that you see down here, is a negative bias. So those two C-cell batteries that you saw, this is running off the negative side, and then the positive side of those batteries goes to the chassis. So this is obviously running to the grids of these tubes. Be interesting to see if those batteries are still good. There's basically no load on this section whatsoever. We'll check that out here in just a little bit. So you can see these rubber grommets here. You can see how they're decayed. So all of that has to get removed. I have to get underneath the tube socket and fix that up. So you can see the amount of work in this already. So somebody's put a pyramid type 3 capacitor into this chassis down here, and it has a squared off end. So I haven't run across a pyramid type 3 capacitor before. These look a lot like Tiny Chief capacitors. So it'll be interesting to put this on the forecasting tester and see whether this is a paper and foil capacitor, maybe die film, or maybe even a poly style capacitor. I'm thinking it's probably paper and foil, but it'll be interesting to see if it's leaking or not. Look at these dwarf midget electrolytic capacitors. So 2 microfarads, DC working volts is 450, and these nice looking little boxes here. So these will have to definitely get replaced. So lots and lots of work. So I imagine what I'm going to do is I'm going to replace all of these grommets. And what's holding these walls on now is just these 2 screws here. So I'll be able to move these out of the way enough to get at these, remove those grommets, and then tighten these tube sockets down properly. So as I have this removed, of course, I'm going to have a little bit more room in here. I'm going to be testing all of these resistors in here. You can see somebody's replaced these resistors in here already. These are a newer Allen Bradley style carbon composition resistor here. These are 2 watt rated resistors. And in this here, you can see we have roundies. And these roundies are probably going to be off of value just a little bit. So I'm going to really spend a lot of time in this area, and I'm going to check everything out, and if anything is suspect whatsoever, I'm just going to replace the components. In fact, I might just do a mass swap out of all the components in this area, because this, again, is an extremely difficult area to get at, and it would be really bad if a resistor way down at the bottom here under this, riveted in, little terminal tie strip went bad or something like that down the road. It's not so bad if other things go wrong in the chassis because they're somewhat easy to get at. But this area here and underneath the wave meter chassis, there's just no chances taken. I want this to be rebuilt, and I want it to stay rebuilt. So 30, 40 years down the road, if somebody else ever owns this thing, it'll still be working. Well, at least this section will at any rate. One other thing, just before I get started tearing this thing down and getting to those horrible rubber grommets and things like that, look at this. This wire is completely disconnected from this choke. I imagine it probably goes up here and it's just hanging off of here like this. So that might be one of the major issues in here. Maybe that's why this thing stopped working. Who knows at the time? Or maybe there has been problems with this thing for a very long time. It's always interesting to run across these things, see exactly what's going on. So we can see that there's another one in here. You see this one here's got a really long lead that runs up to here. So I'm imagining that this probably goes up to here. I'll have to check that out on the schematic and see exactly where that goes. Just get a little bit more light in here. So, and that high voltage bus runs around and then comes back through here again. So there's a lot of rubber grommets in there that need to get replaced. Lots and lots of stuff. There's another replacement capacitor under here. You can see that one there. So the more I look at this, the more issues I see that have been taken care of over time. So it'll be really interesting to test a lot of these components and see how bad they really are. Again, somebody not long ago put a BNC in the front of that, and they were trying to use the scope, and that's what this chassis is for, right? This is for the scope. So somebody was trying not too long ago, and you can tell by this as well, that they're trying to operate this thing or trying to run it. So not a good thing, especially with that exploded capacitor in the power supply, right? When you're starting to work on a section like this, the best thing to do is just tackle one section at a time. You don't want to really start pulling a lot of parts and pieces out of an entire unit like this, because after a while, once you start removing all of these little parts and pieces that are just connected everywhere, you'll work, in depth on one little section, and then you'll come to the next section and you'll go, oh, there's different parts in this section and they're connected in different places. So you don't want to make things confusing, and this is especially important if you don't have a schematic. Now, I managed to find a schematic on this, and I've looked at the schematic, but it looks different than this unit here. I think this is an earlier unit, and we'll take a look at the schematic here in just a little bit. So the first thing that I want to do is get these capacitors out of the way. You can see how far down they are from the top. So what I'm going to do is clip this here, and then I'll desolder this and then pull the end of it out so that I have a nice little eyelet here again, so I can reuse that. And it's the same with down in the tube socket here. I'm going to desolder this here, and I'm going to check all these resistors too, just to see how close they are. So I'll test this one here. This is connected to this same area that these two capacitors are attached to. So this is green, black, orange, so that's 5, 0, and then the multiplier is 3, so that means put 3 zeros in that place. So it's 5, 0, 0, 0, 0, so that's a 50k ohm resistor. So a modern replacement for this 50k ohm resistor would be a 47k ohm resistor, and it'd be absolutely fine to use something like that in this resistor's place. But we'll test this here in a little bit, and we'll take a look, see how far off value, if it is. So what I'm going to do now, I guess what I'll do quickly here is I'll just clip this, just like so. I'll loosen this up right here. And down in there, it looks like I would probably have to tackle with this as well. So I'll get the capacitors out of the way, and then what I'll do is I'll spend some time with the desoldering tool and my soldering iron down in here, cleaning off that tube connection down there so I can put the new components in. So I gotta get this way down in here. This is pretty much shutting my clippers. Move that out of the way. I can just pull these two capacitors out of the way. If I can get it past this little tie strip here, this little eyelet. There it is. So those are the two capacitors. We'll also take a look at these in just a little bit, just for the fun of it. We'll see if these capacitors are even working still. Be interesting to see. The blowhole hasn't ruptured in this yet, so that'll be kind of interesting to find out. So now what this does is this allows me to get right down inside here, right down to that little area, and desolder this. And I can also desolder this area right here. So actually what I'll do is I'll just do that right now. There it is, and that eyelet is nice and clean now, so I can solder the new capacitor to this point. I'm going to use, obviously, more modern style capacitors in here. So what I really want to do first, what I want to do is be able to get to these screws so that I can take these old rubber washers out of here and then tighten the tube socket down. Now, since I'm going to be using new capacitors, I'm going to add another eyelet like this over right to this tube socket connection. And the new capacitor that I add will have shorter leads, and it'll attach right from this connection here right to that ground there, and the capacitor will lay down here. And then the other capacitors that I have to locate the outside foil yet, is I will attach that one to this old point here. So that should work out really, really well. Let's test some of these resistors and see how close to their values they are. So we talked about this one here first. This one is green, black, and orange. Now this is something that can get very tricky. There is no silver band on these, so that means that these are 20% tolerance resistors. Now we look at this one first, green, black, orange, and we know that this is 50K, so we come over here and test this one, and this one is orange, black, green, very close. So if you discover this one first, this is a 3 meg resistor, you might accidentally put a 3 meg resistor over here if you weren't paying attention to the way that these colors go. It's a real common error, common mistake. You need to be very, very careful. So you can see that this one here has been replaced or opened and tested at one time. You can see that they've done the J-hook thing, cut the resistor open, and then they've taken the leads and then soldered them together like that. So let's see how close to 3 megs this resistor is. 4.1. That's quite a ways off. I'll move the focus over to the meter here. Get a better focus on the actual meter. Let's try that 50K ohm resistor here. Right here. So it ties to this area and right down to here. Yeah, 68. Got to get a better connection on that socket there. There we go, 68.3K. That's a long ways away from 50. Yikes. So yeah, you can see all these resistors are just in outer space, right? Sometimes the lower value resistors, like these, they hold on to their value. Seems that, the lower in value they get, the closer they are. So this is 2.2K. Let's see what this one is. 2.4. Not too bad. Here's a newer Allen Bradley style resistor. Right here. So let's see what it's going to measure. This is 4.7K, by the way. 4, 7, and then 2. So this is the multiplier. 2, so that's 2 zeros. 4, 7, and 2 zeros. 4,700 ohms, or 4.7K, and the silver band means that it's 10%. So 5.1, 5.2, candidate for replacement as well. Let's see this one here. There's a large roundy. That wire out of the way. Focus on this one here for a sec. So you can see this one here is 2, 2, and then 3 zeros. So that's 22K ohms this resistor should read right here. Okay, so let's test that out. Whoa, 400K ohms. I would say that this resistor is very far off, definitely exceeding 10% tolerance. So for a resistor like that, that's basically considered open, right? So 22K all the way up to 400. So this would definitely be a huge problem in this vertical amplifier section for the oscilloscope. So a bunch of different issues in here. This definitely would cause some big, big problems. So it was not up to anywhere near working condition. Let's test this 10K Allen Bradley resistor down here. So this is 10K hiding under here. You can see brown, black, and then orange. So 1, 0, and 3 zeros. That's 10K. See if I can get my probe down there. Try that. Oh, come on. 10.8. Not too bad. So, yeah, this whole area needs to get rebuilt. Everything will just get replaced in here. Again, not taking any chances, right? So, but it is fun to see how far off these resistors are. There's another one hiding down in here. So that's 2, 0, and then 5 zeros. So this is a 2 meg resistor. Let's see how far this 2 meg resistor has moved. Right under here. To there and to here. There we go. 2.1. Actually not too bad for that one. But still, they're all out of there. So there we go. We got a good idea of how bad this vertical amplifier section actually is. So get rid of all of these components in here. And then what we're going to do is fire this thing up on the bench. So I'll hook the filament leads up and find the B+ and give it some negative bias and find out where these leads go. So these leads here and these leads here exited out of those little rubber grommets on the side. So I'll find where these go, probably to VR switch or something like that. I'll find out how that works and then hook them up appropriate. And then we'll feed a signal into this section and take a look at the output and make sure that this is operating 100% before this thing goes back into that frame. I've started the disassembly procedure for the entire vertical deflection amplifier in the Supreme Vedolyzer, so I'm going to strip this thing right out. Now, this vertical deflection amplifier is so different than what's on the Vedolyzer schematic that I have. I had to reverse engineer this before I started to take this apart. So when this was all together, I just spent some time, put this on the bench, and drew this all up and made another schematic for this section. So in the end, once this is all rebuilt, we'll take a look at that schematic and we'll compare it to the actual Vedolyzer schematic. I think what's happened is this is an earlier version, and the schematic that I have is for maybe a later run of Vedolyzers. It's so different that it's actually missing one of these tubes. So the newer version only has 3 tubes, and they're using somewhat of a brute force method to drive the CRT. They're using a 6L6 to do that. Whereas, this is, I could say, a little bit more tame than that. So what I'm doing is, I'll grab these 2 shields here. So this is one of the shields here and one of the shields here, and they just fit like this. You can see I'm numbering them as I go along, things like that. So what I would do is I'd just remove all of the components on this side of the shield and then take the components out of this eyelet here, which is on this terminal tie strip, clip the rails, so the B+ rail and the negative bias rail, and then remove this. Remove all the components in here, get that all done, remove what needs to be removed from this eyelet here, clip the rails again, and then remove this one. And I'm just going along like that, just basically stripping it right down. Now, I'm going to leave the filament lines on the tube sockets because, what's the point in removing them? I'm just going to have to put them back on again. I'll leave all of these lines on as well because these all lead off to separate parts of the circuitry. So I'll get all of these off, basically stripped right down, take all the tube sockets off the chassis. So all I got to do is just remove all of these screws and then desolder these wires here from these eyelets that are riveted to the chassis. And then I can just lift all the tube sockets right out, and I'll put new grommets in each tube socket and just kind of lay all 4 of them back in, put the screws in. And then I have some nylock nuts that I'm going to use on the back side here that'll never back off. And that'll work really well for that. And then just start the reassembly procedure here and get the whole thing back together. This is what one of the assembly line workers would have seen way back in the late 30s. So this would end up coming down the line, and there'd be a person that would put on all of these ground eyelets here and then put the rivets through with all the star washers. And then this would go down to the next person. And this could be made on a jig just like this. And be a good reason for the squaring off of the wires so nicely. Probably screwed down to a jig very fast, and then they would wire it up. And then this would come to the next person, and they drop this in place, put all the screws in, and then this would go down the line again. And then they may start putting these things on, start putting on the little shields and everything. So that's what this looks like, stripped right down to nothing. And as you can see, there was a problem in this area. You can see this discoloration here. And we can also see the discoloration on the wires. Now the choke that was in that area is pretty cooked. So that resistor that was in the center of this got extremely hot for some reason. Look at that. It's turned all white. And the windings on the form here, the form looks like it's actually shrunk. It's got so hot that it shrunk, and you can see between the windings and the form there. So if you're to look right here and on this side, you can see that gap there. There's not supposed to be a gap there at all. So this is actually shrunk. Now, whether this is still okay, maybe the actual form just got hot and the windings are okay, I'll have to test this out. So this really, got another one here, should look like this. Right, so that's how a good one looks. So you can see that this has definitely gotten extremely hot. So I'll have to end up measuring this one here if this is bad, and then take this value and try and mimic this here. Again, we want to see how this thing is going to work, as it rolled off the factory floor. So that's where I'm at now. Now to start all over again. Through the magic of the camera, days worth of work becomes seconds. So rebuilding this section was an incredible job. It took a lot of time, but since this is going to be a permanent fixture on the old-time workbench, it's worth it. We're going to be servicing all sorts of equipment with this old piece of test gear. Should be a lot of fun. Now, a lot of thought went into the rebuilding process of this vertical deflection amplifier. As you can see, there's components everywhere. Shadows of the capacitor makes it look like there's double the amount of capacitors in here. So nice shiny plates on here. So a lot of thought went into this, and what I'm going to do is just fill you in on the highlights, because I could spend an incredibly long time filling you in on why I've moved components where I have and why I've mounted them and all sorts of things. So I'll start with the tube sockets here. All the tube sockets have brand new PVC grommets. I used PVC grommets because they last longer and they are a little bit more rigid as well. I've used the nylock nuts, as you can see down here, on all of the screws. So nylock nuts is basically just a normal nut with a ring on the top and a little nylon disc in there. And when you wind the screw through the nut, when the screw comes through that nylon washer, it pinches or squeezes against the screw so that the nut doesn't back off. So those are very handy, especially when you're dealing with, a rubber grommet underneath where the tube socket isn't, incredibly tight. Now, even tightening the tube sockets down took quite a bit of time. Reason being is when you're tightening down these nuts, you don't want to squish that PVC grommet. You want to tighten the nut down just to the point to where it's snug on the grommet so that you can feel resistance. And of course, the tube socket isn't wobbling around. If you tighten the nut down too tight and you squeeze the grommet, they'll end up cracking down the road. And not only that, what's the point of having them if the tube socket is just completely solid there, right? So just tightening these things down, basically looking like this. So what I'm doing is I'm looking at the little grommet, top and bottom. So I don't think you can see that. Maybe if I get a little light here, you can maybe see on the underside. If you can see on the underside there, see if I can get that in the camera. So there's the top. You can see the little grommet there. Both top and bottom, you can see it's not squished. You can see it's just snug. That's about the best lighting I can get. Maybe I can move this around just a little bit. There you go. And they're all like that. And even on the top, you can see that little bit of the nylon on the nut in the top here. Right on the top there. See a little bit of the nylon there, red nylon. So all the tube sockets have got brand new PVC washers or PVC grommets and nuts and even screws. I used stainless screws to hold the tube sockets in as well. So that's all been done. All the grommets that you see in these plates here are the same PVC style grommet. You'll see that there's some of this silicone heat shielded pipe that I'm using in the center of the grommets. Now I can still move this around. You can see how I can slide that around a little bit. It is tight, but I can slide that around. The reason that I have this pipe over this copper wire here, this is a piece of number 14 copper wire that runs through here, down here, and then it runs through the bottom, and that powers up the screen grids as well. Those 47k ohm resistors that you see there all run to the screen grids. So the reason that I have these little pieces of pipe on here is when you solder to a piece of copper, copper conducts heat very well. And what ends up happening is if this piece of number 14 wire is on one of the grommets, there's a chance of it melting into the grommet or moving down through the grommet. We don't want to get the B+ line close to the chassis. So by putting a little bit of this heat shielded pipe on here, so this is high heat stuff, it's like the stuff you find in your toaster. Putting a little bit of a, just a little bit of a shield on each one, just as the grommet goes, or the wire goes through the grommet, allows me to, have quite a bit of dwell time with my soldering iron here, and I don't have to worry about melting those PVC grommets. And you can see they're everywhere. They're on the negative bias line for the grids, and they're all the way through. So down there you can see them and all over the place. So this one here, this is just basically the wire just runs through here and then down through here. So I used a long piece of pipe that protrudes through the grommets on the ends. Now, what they're doing in this section, it looks like what they're doing is they're tuning they're tuning the last two stages here. And they're using these, what basically is a choke. And what they're doing is they're putting a resistor through the center of that choke. And the last one in this section here, as you saw in the previous shot, was pretty melted. That resistor got really hot. And chances are the reason that resistor burnt up is one of the original wax capacitors was so leaky that it was drawing excessive plate current, and it heated up that form to a point to where it actually just fell right off. I think I have have that right here. So it just basically fell right off the form. So surprisingly, this is still good. So the form burnt, but it didn't affect the actual little windings here. But since this isn't on a form and it would just be kind of hanging, I don't like that. So what I did is I measured these, and we'll take a look at the schematic here in just a little bit. And I found a suitable replacement that has its own little housing here. So basically what I've done is I've taken this, there's no current pass through this. So I've taken this and I've put a new one in this side here, and I've ran the wire down to where the original choke would go. And now the resistors sit external to this, and I've doubled up on the resistors there so that, you know, it's going to run just, well, let's say the original resistors, you know, would get pretty hot. So having two of them in there like that basically just makes it not so incredibly hot in that area. The resistors don't get so hot, I should say. So that is the replacement for that, and this is the exact same reading. So I measured the original little coil in the form on my Genrad, and then I compared a whole bunch of little chokes and coils that I've got, and this one here is extremely close. So I put that in there. We'll get to test that out here in a little bit. You'll see that I've added these two standoffs here. I've added a standoff here, and you can see that this piece of copper wire comes out to the standoff. Basically what this is doing is this is just holding this tight. Before they had a piece of wire with a little loop in it, and it could move around in there like this. So by having this on this standoff here, it holds this really tight so this will not move around. And it also gives me a more solid place that I can resolder the wires from the B+ to this area right here. Now, this one here was still in good condition. I removed the resistor from the center of the form, and I put a metal film resistor of the same value in the center, and I put a little bit of super glue on it. And then what I did is I put 100 volts across that 2.2 k ohm resistor for a very short period of time, and the glue set very fast. So that's all one piece now. Now, one thing that they did, which I really don't like, is you can see the winding, it runs off here, and I put this on a standoff, so now this is nice and solid, so this will never break. You know, it won't get tugged on, or if you run your hand down in the chassis, you're not going to bump it and snap it off the little form there. What they did at the factory is they just had this little thin wire running right to the back side of the chassis, so if you move your hand down in there, or you drop a screwdriver or something like that, you can completely destroy this. So this is the same value as this up here, 150 microhenries. So what I did is I took that and I put another little standoff here, and then there'll be a jumper wire from this point going to the back of the chassis, so this is solid and this won't get disturbed. Let's see, what else can I tell you here? I moved a lot of these capacitors around. The screen grid bypass capacitors, I've moved them around. Well, there's a whole bunch of reasons for this. Some noise considerations and things like that as well. Not only that, by having this side almost completely free, I can get a soldering iron down in here on so many different angles now, and I won't bump into any components. If I need to remove a capacitor or a resistor down here, I can almost get to this in any way, shape, or form. So I can run the iron down in here, and if I need to, say, remove a screen grid resistor, it's just right under here. I can, you know, basically get my iron in right in there. So it leaves a lot of room. So a little bit of component movement. If something was to ever go wrong with this in the future, you know, again, I don't want to remove this from the chassis because it is a real pain, right? You gotta remove the wave meter, and basically you have to take the face off the unit to get the wave meter out, things like that. It's, you know, just an absolute crazy job, right? So I've used very high quality electrolytic capacitors, all high hour electrolytic capacitors, 105 degree, basically the best stuff I can put in here. As you can see, I've located the foil side, the little dots on all the capacitors. I do that, which marks the foil side, so it doesn't deface the capacitor, it's just a little dot, and I use the sift device to do that. So those of you that haven't heard about the sift device, it's something that I've created and put on Patreon. It allows you to identify the outside foil layer in these newer capacitors because none of them are marked. In the ones that are marked, some of them are backwards. Odd. At any rate, so that's all done. There's so many things. So at this point, I'm pretty much ready to test this thing out. So what I'm going to do is I'm going to grab the original schematic for this, and then I'm going to grab the schematic that I drew up. So the original schematic I found is different than this. So again, as I mentioned earlier, I think it was an earlier, or I think this may have been an earlier model, and then the schematic was maybe a later schematic. I'm not sure. It'll be either or. I guess one day I'll find out. I think that's revision C, actually, it said on the schematic, so this may be an A. Again, so this might be earlier. So I'll get the schematics here, and we'll take a look at the schematic, and I'll do a little bit of comparison for you, and I'll show you exactly what's happened here. This is a factory schematic for the Supreme Vedolyzer. And as you can see here, in the vertical deflection section, they only have 3 vacuum tubes. They have 2 1852s and a 6L6, pretty much in a brute force, I guess you could say, vertical deflection section. So really what they're doing is, they have low value resistors here, 2500 ohms, 1 watt, and then they have a choke. So they're really cramming, the signal through here. So this is a wideband amplifier, kind of built to a minimalist kind of approach. So the vertical deflection section in the unit that we just looked at is quite a bit different. They have 4 vacuum tubes, and they actually spent the time to tune certain areas. Now, really what these things are is they're just RF chokes, but in this case, since they're using this to tune little areas, you could call them coils, I guess. And what they're doing is, these tubes aren't working as hard. There's, much higher value resistors here, and basically spending the time to make the section work efficiently. And we'll take a look at that here in just a little bit, and I'll show you the effect of how coils tune things. So I should be able to do that with some isolation capacitors and things like that. I'll get to that with the oscilloscope here in just a little while. So taking a look at the vertical deflection section, this is basically how this is. So this one section here is this area here, and then this section is this area, kind of in the middle of the wall, and then this section, and then this section. It kind of moves along like that because the wall's kind of in the center of the tube socket, right? And really, when you look at this, all this is a wide band amplifier. So you can look at it like an audio amplifier, but would go way beyond the audio spectrum. So, this would go up into the megahertz. It should work fine up there. Now, they have 4 stages here. This stage here looks a little bit funny. They have, at least the factory values, what I found in this vertical deflection section is 110K and 16K. And they run the bias to the control grid off to somewhere else, and the cathode is also ran somewhere else. Now, if you were to have negative 3 volts bias on a tube like this, you're going to have extremely low plate voltage here because the tube's going to be on, and this is an awful lot of resistance here on the plate, especially when you have a screen grid here. So it's going to pull a plate down to nothing. So I imagine that they're biasing this a little bit different, or either that or somebody has been in here and done a really good job at changing these resistors. So they looked really factory. So once this is back in the actual Vedolyzer and it's in its final test, we'll end up testing all of that out and see what happens. You can see the resistors are very easy to get at in this section here. If I want to get rid of this, basically just heat that up, lift this up, and I can remove this resistor or the one down below as well. Again, the placement of the components and moving things around makes, for easy servicing in the future. So very interesting. Now, the whole section looks like it's, pretty well done. Somebody was in here and they did a bunch of, silly things, so I just omitted all of that from the schematic. So this is as close to what this very well could be as I'm going to get, right? Unless somebody's been in here and say in 1950 they did some modifications or something like that. But the rest of this, it looks like it should work very well, and this will probably work as well. We'll be able to probably fit signal through this and all that. So we'll get to that here in just a little bit. We'll end up hooking this whole thing up and trying the thing out. Try it on the bench first. So there's a bunch of wires that are loose. You can see I've got green here, and then I have yellow here. So you can see, there's green and yellow leads, and they all go to different areas. You see there's a yellow lead over here. Now, this yellow lead here runs to the cathode of this tube, and then we have the yellow lead, which is over here, which is running to the control grid of this section here. And there's a green lead. See this green lead right here? This green lead is running off the plate of this tube. So in order to attach this area together, I looked in the Supreme Vedolyzer chassis, and these two leads here, right? So these two leads here just run out, and then they go through some very, very light valued capacitors, 16 picofarad each, and they're in series. So that's going to turn out to be about 8 picofarad across that. So there'd be about 8 picofarad of coupling across this. And then there was a black lead in the center that runs off to a wafer switch. So I don't know, they might be using this in the wave meter section. So I haven't traced that out yet. So in order to pass signal through here, I would just grab a random value, maybe 22 picofarad or something like that, and just bridge it across here, so that would get signal through here and then into this stage. So I need to put a 22 picofarad, we'll say that, capacitor across this, so that'll get these two wires occupied and into the circuit. So then we go into this amplifier stage here, which is a nice broadband amplifier. You can see that this is somewhat like what they've done here. You can see in this brute force method here, they've got a choke and then, a rather low value resistor, 2500 ohms, 2.5 k ohm resistor. So, and it's 1 watt. So, they're putting quite a bit of current onto the plate here. It's probably going to get pretty warm. Kind of doing the same thing here. Value's a little bit higher. 410 microhenries is the rating here. 7 ohms DC resistance. So I measure the DC resistance as well. So if you have one of these things, this may help you out if you're trying to troubleshoot a burnt choke or coil. At any rate, so this is just a wideband amplifier. Signal's going to come in here. It's going to get amplified again and then come out of the plate. And then we have this going over to the yellow. Now these two leads run out again. So now we have these leads here. We have a yellow and a green lead here, right? So this yellow lead, I could directly just connect to this because there's a capacitor here and there's another, rather large value capacitor, 0.5 microfarad. So I can just connect those two together just like this, and that'll get the signal into this stage. There's blocking capacitor and everything. One thing that's really interesting about this is they've got a 2.2 k ohm resistor from the yellow lead here right to ground. So they're taking a signal that could, be have quite a bit more amplitude, and they're pulling it right down. So they're using this as somewhat as a gain limiter on this stage. So they may have found in the design of this with the 4 stages that it just had so much gain they needed to clamp it down, and that might be the reason that they redesigned it for 3 tubes. So yeah, so that's really odd. 2.2 k ohms is a really low value to have pulling a signal down at that point. Kind of interesting. So the signal then goes into this stage, and again we have another amplifier here, and we have a tuned section. So remember from the earlier videos, signal goes in the grid. This is the control grid, and out the plate. So we have the control grid, the screen grid, and the suppressor grid. You can see the suppressor grid is just directly grounded. Suppressor grids are usually either just directly grounded or connected to the cathode inside the tube. So these ones here you can actually just separately ground out the side. So we get amplification again out here on the plate, and as you can see, it's tuned. Our signal's going to go through here, and this is just directly connected over to here. And again, we have another amplifier in the grid and out the plate, and then this one here would run out, and probably at that point would be somewhere in this area here. So it would go over to one of the vertical deflection plates in the CRT. So just a bunch of tuned stages. There's a bunch of goofiness going on in this stage. Somebody had bridged a resistor right across here to here, and that's just going to wipe out all the gain in this area. So that was definitely an add-on. Somebody had done that. And of course this lead was open on this little choke here. I found out was just basically open, right? So Lots of issues, and this 22k ohm resistor, that original 22k ohm resistor, I think it was 400 and something K. So if there's no voltage on the screen, the tube is just not going to do anything. So there's, you know, it won't amplify at all. So you have to have screen grid voltage, right? So lots of problems in this one section here in the amplifier originally. So hopefully now this whole thing will operate. Down here we have a negative bias. This is where those two batteries, those two, I think they were ever-ready batteries in the chassis, those two negative bias batteries will just connect to here. Now, since they're going to the grid connection here, and you know there's brand new capacitors here, there's going to be no real leakage or anything like that. Negative bias batteries will last basically until they rot open or till they start to leak. So negative bias batteries, there's, you know, no current being drawn whatsoever. It's, you know, again, vacuum tubes are like FETs. They're voltage-driven devices, right? So this is just basically giving the negative bias to keep the tubes shut off when they don't need to be turned on. And these were the values that I found. So the values that I've used for this now are the nearest closest modern value. So 3 meg would be 3.3 meg, 2 meg would be 2.2. I used a 560k resistor in this area here. That's close enough to 610. That'll be fine. 47k ohm resistors are installed where the 50k resistors are. That'll be absolutely fine. Things like that. Doesn't make a whole lot of difference in these circuits. I know a lot of people think that you need to be exactly right on the money. You got to be right on the mark with all of the components. It isn't like that at all working with vacuum tubes. Not at all. Unless the actual circuit is an extremely, I guess you could say tight tolerance type of circuit, say it's in an oscillator or something like that. Changing capacitance values in an oscillator is the world. It means everything. But in an amplification chain like this, you know, it's just not too big of a deal whatsoever. They've changed these capacitors in the more modern schematic. There's an 8 here, and then they still had a 2 here, I think. There's a 2, yeah, a 2 right here, but most of them are all 8s, and there's no reason that they can't be all 8. And of course, the nearest value to that is 10. So all of the new capacitors, all the bypass capacitors here on the screen grid and everywhere along here are all 10 microfarad. Again, absolutely fine. And a 0.1 microfarad here. So low frequency and high frequency bypass capacitors on each one. That's the reason that they have 2 capacitors on the same area. You'll see 2 microfarad and 0.1, so low frequency and high frequency bypass. That's basically what they're doing. Want to make sure that these stages stay nice and clean, and as you can see, they did spend a lot of time. You know, everyone has its own wall, right? Want to make sure that everything is running just the way it should. And, you know, this unit has a wooden case. There's no even metal case around this thing, so they had to spend all that extra time in the design to make sure the thing did stay nice and quiet. So now what I need to do is feed a signal into this thing to test this out. So I'm going to put the tubes in this. So we need to feed a signal in here. So I'm going to put a blocking capacitor on the grid, and I'm going to have to tie this grid somewhere. So I'll probably just tie this to this -3 volts. So again, you know, I'm going to probably have very low plate voltage. I'm going to have to take the cathode and ground it just like these ones. So this area right here, what you see here, will go to just with a jumper cable over to here. This is the -3 volts, the bias. And the cathode, which is this, will just get clipped right to the chassis. So that gets rid of that. I'll put, we'll say a 22 picofarad or close to value capacitor between these 2 wires. Just leave that floating there. These 2 wires here will just get connected, and we should be able to get signal all the way through here. Here you can see that this coil is just running directly right off of the plate, so there's going to be full B+ here, so I'm going to have to put an isolation capacitor here as well, and that's this point right here. So I'll have an isolation capacitor coming out of here, and I'll even put another little capacitor on the plate lead right down here, and we can see the effect of the tuning. I'll move the probe lead from this side to this side, and we'll take a look at the amplitude difference between both sides. You see how they're actually using this to tune. Then I need to get B+, so I'll have to put B+ here. Now on this schematic, I'm pretty sure they're probably using the same B+ and the same transformer and everything. So they probably didn't retool for that, I'm sure. So it's 360 volts. So what I'll do is I'll take the my regulated power supply and turn it to 360 volts. So that will go to this point right here. I'm going to need a heater supply, a 6.3 volt heater supply. So this will run over to that tap on my regulated power supply. I need a negative 3 volt bias supply, which will clip right here. So there's going to be lots of wires running to this thing. It's going to look like it's on life support, really. And then I'll feed my signal generator into this end, and we'll take a look on the oscilloscope at this end, and we'll take a look at the difference in amplitude. So what I'll do is I'll just get that all set up now, and try this thing out, and hopefully it works. That's a lot of work if it didn't. I'm just about ready to try this out. I'll show you how I've got this hooked up so far. In just a moment, I'll show you how I've got all the wires running off to the power supply. So I've got that 22 picofarad capacitor just tacked into these two wires, just have it hanging in the breeze right here like this. These two wires are just connected together, so they're just soldered together. I've taken the negative bias and I've ran it over to the grid resistor here on the first stage, so the negative bias is here. It's coming in through this green lead here, and then it just runs along here, and it's running over here to this resistor. This is where the signal is going to go into the first stage, so my signal generator will clip onto this. So the signal lead will be here, and then just to the chassis. Out here on this side, I've got these two capacitors right here. So this one here is right off the plate, and this one is on the tune side, so we can look at the difference in amplitude on each side of that coil. You can see here I've got all the tubes in. I haven't even taken the dust off the tubes yet. I've just plugged the tubes right in so we can test this out. So all the tubes are plugged in and it's ready to test. As you can see, those rubber grommets act as shock absorbers for the vacuum tubes. So those tube sockets kind of float there, and that's what they had intended in the first place. So interesting setup, very, very interesting setup. So that'll just sit like this, and I'll end up testing it like this right here. So what I'll do is I'll reposition the camera and get the oscilloscope started and everything. Let's try this thing out. I have the vertical deflection amplifier attached to the power supply, and just the heaters are on right now. You can see all the wires all over the place on the bench. So even with just the heaters on, you can see how hot those tubes get. When you turn the B+ on, they get much, much hotter. So a word of caution when you're working around these vacuum tubes. I've seen the paint on the tubes actually wrinkle. That's how hot these metal tubes get. So you definitely don't want to ever brush your hand up against them because you get a really bad burn. So what I'm going to do is turn on the power supply here. You'll hear a click. Everything is set on the power supply. So what I'll do is I'll just show you the power supply. And I'll just move the focus up there, and I'll zoom on in. So you can see it's about 360 volts at about 70 milliamps or so. So drawing quite a bit of current, but there are 4 vacuum tubes on that chassis. The negative bias is set as well to negative 3 volts. So let's take a look at the oscilloscope here. That's all attached into circuit as well. Zoom on into that. So the yellowy looking trace on the top is the input signal, and the blue trace on the bottom with the little arrows chasing around is the output. Now I have my signal generator set to 1.5 megahertz, and the output of that signal generator is in the very low millivolts. So what I'll do is I'll plug the cable in. I have the cable unplugged. Just plug it into the signal generator right now. And as you can see on the top, 3.1, 3.2 millivolts peak to peak is giving us an output signal of 149 volts peak to peak. I'd say this amplifier is working very well. Now, I've got the output attached right to the plate of the vacuum tube. It's not going through that coil, so it's not tuned. So as you can see, it's at 149. That's that blue trace and the blue writing on the side there. at 149 volts peak to peak. Now watch what happens when I move the oscilloscope probe over to the tuned side of the coil. So keep in mind 149 right now. So I'll disconnect the probe and attach it to the other side of the coil. Look at that, almost 170 volts peak to peak on the tuned side of the circuit. And that's the reason that they put those little coils in there. So it's a very sensitive amplifier up here. Works very well. As you can see, little signal, 3 millivolts, is giving us crazy output. I'll turn down the amplitude of the signal generator. You can see down in the microvolts, we're still getting 45 volts peak to peak out. The reason the traces are jumping around like that is because, the circuit's wide open, it's laying on a bench, and there's wires hanging all over the place. That's the reason that you're seeing that noise right now. So that'll all disappear when the thing's back in the chassis, right? So it's working extremely well. So Project Vertical Deflection Amplifier is complete. It can go back into the chassis, and I can get on with the rest of the restoration. I hope you've enjoyed part 1 of the Supreme Vedolyzer restoration process. Sure has been quite the adventure already. Part 2 of the Supreme Vedolyzer restoration process is coming up very soon. So if you haven't subscribed, now would be a good time to do that. That way, when part 2 is launched, you'll get the notification right away. And don't forget to ring the bell as well. If you're enjoying these videos, you can let me know by giving me a big thumbs up and hang around. There'll be lots more repair and restoration videos coming in the near future. We'll be taking a look at vacuum tube and solid state equipment alike. If you're interested in learning electronics in a different and very effective way and taking your electronics knowledge to the next level, you might want to check out my Patreon electronics course. I'll have the link just below, pinned at the top of the comments section. So click on the link and it'll take you right there. There's a lot of really good people there. Once you are there, check out the community section. Lots of people are sharing their projects and ideas as well. As soon as part 2 to this video is created, I will put that part 2 under the Show More tab in the description of this video. So just below this video will be a description, and you'll see a little Show More. Click on that and it'll expose the link to part 2. And that, of course, again, is when part 2 is finished. All right, until next time, take care. Bye for now.